So we've seen this idea where we're going to build up molecular orbitals by using atomic orbitals, and really to describe any organic molecule by molecular orbital theory would be great, but it's prohibitively hard to do because of just how it works. You would actually need a computer to solve it. So there is a simplified tool we can use to guess as to what's going on with these orbitals that are formed in our conjugated pi system. So to do this, we're going to use what's called a Frost circle. Now in a Frost circle, as the name implies, we're going to draw a circle. And the midpoint here represents the energy of the atomic orbitals themselves. So basically, any electrons sitting at this level do not see a benefit or disadvantage to being in molecular orbitals. Now, let's start simple. If we have two butene, we have two p orbitals that are being used in order to generate bonding and antibonding orbitals. So the p orbitals would sit here, and we'd have one where they're in phase, the bonding, and then we'd have the antibonding, ABs. So a Frost circle is going to approximate the energy of the orbitals we expect to see relative to the base p orbitals that are being used in terms of the molecular structure. So how do we use this? Well, let's make our system bigger. So, sorry, I'm going to try to draw a benzene ring on its side. So let's say we have something like this structure here. So we're going to use the p orbitals associated with this pi bond and this p orbital here. Well, now we've got 3. And the way it's going to work is that we're going to draw, based on the number of p orbitals that we're using, we're going to draw the associated geometry of something with that many sides. So if we've got 3 p orbitals, we're going to draw a triangle, and we're going to put one point at the very bottom. So for something like this, where we have a double bond in this, we'd actually end up with one bonding orbital and 2 antibonding orbitals. Now, the number of electrons in this, we would just add up based on the number of pi electrons and p electrons. So in this case, we've got 2. If this were a carbanion, we would predict that we'd have 2 in the antibonding, so this structure would be stable. Let's say we added another one. Let's say we did a structure that looked like this. Well, in this case, we've got 4 p orbitals because we have 2 pi bonds. 1, 2, 3, 4. So we'd end up with 1, 2, 3, 4. Now, how many electrons do we have? We've got 1, 2, 3, 4 electrons. So in a structure like this, we'd expect to have 2 in the bonding and 2 in the non-bonding orbital. And to make something that would resemble an aromatic, let's say we have 1,3-cyclobutadiene. This would have a similar structure to these atomic orbitals, or to this approximate molecular orbital diagram. So this we would say is non-aromatic or anti-aromatic. And the reason why it ends up being anti-aromatic is that we have 2 electrons in what are called non-bonding orbitals. These electrons basically exist in a place where it doesn't really have an advantage or disadvantage to being in the molecular orbital relative to the starting p orbitals. Now, let's say we do benzene itself. So benzene has 6. We're going to draw a hexagon. So we got 1, 2, 3, 4, 5, 6 orbitals. Now, 6 electrons. 1, 2, 3, 4, 5, 6. So in terms of the orbitals associated with that conjugated pi system in benzene, we see that we've got 6 molecular orbitals we could generate. 3 are bonding, 3 are antibonding, and in the case of benzene, we actually have all 6 in bonding orbitals. So that's what makes this compound aromatic. So what the Frost circle allows us to do is guess where the electrons are going to be in the conjugated pi system. And as long as they're all sitting in bonding orbitals, not in non-bonding and not anti-bonding, we have the potential here for aromaticity. So next video, let's talk about how we can use this to draw that 4n+2 rule and where it actually comes from.